Well, hello everyone. I am Bogdan Stan. I've been working as a software engineer for ING Hubs for more than 10 months by now. I'm a cloud enthusiast, and what I like the most is being engaged in community activities, which made me learn a lot of things during the years. Now, okay, he's having fun. We'll see first why stability often tricks us. Then we'll see what is chaos engineering and what we can do with it, followed by a short demo with 3 experiments and some key takeaways for you to follow and to take home in your own chaos journey. About my current working environment, ING Hubs Romania is one of ING's global capabilities with a focus on technology. We offer more than 100 solutions to our 24 ING units worldwide. We have more than 2,000 employees active in software development, data management, touchpoint integration and channels, core banking, and global products, all working to enhance banking worldwide. We have a lot of experts, like software engineers, DevOps, data, product and business, and obviously risk and compliance, because, yeah, we are a bank. Here, like in my whole career, I often felt inspired by people that do their job with passion, which leads us to this personal quote. Yeah, it's my quote, which means that chaos is the raw matter of the universe, and as us, even the universe had to learn how to use it to create something great, which also represents why we are all here today, to create something great of our own. Right now, I am part of a great team. We are not working just on maintaining our application code. We are working on our infrastructure means, like HPAs, multi-AZs, and killers to provide stability. But as we know that stability is often an illusion, we architect to perfection by discovering key problems in our clusters. We know that we often feel safe about our deployments, but today, let's all do a challenge and stop running from failure and instead let it be chaos. I don't have the sound. Okay, we've all been there. Everything was green on the dashboard until a network partition or a memory leak hit. The problem is not that things are breaking, it's that we don't know how and when they will break until it's too late. It's okay. No, it's okay. The sound is okay. The 3 AM phone call is not about our monthly on-call routine. It's about unexpected problems that can appear in our clusters, like pod failures, network failures, network loss, cloud providers down, or even our grandma having her sweet, sweet apple pie catching fire in the oven. Chaos engineering is often misunderstood. It's not about being a chaos monkey and breaking things randomly. It's about building confidence into our systems and do some disciplined experimentation and proactive identification of failure. Think of it as a vaccine. We inject a small amount of harm to train our system to survive the real thing. To move from just breaking things to real chaos engineering, we must follow a 4-stage scientific loop. First, we start by defining a steady state, our definition of how a healthy system should look like. Not just like a low CPU, but meaningful business metrics that can appear in our clusters, like a P99 latency under 2 milliseconds for our microservices. Then we form a hypothesis, our measurable prediction of how our healthy system should look like under stress. If, as an example, if we terminate a node in the eastern region, the traffic should fail over to the western region under 5 seconds without any human interaction. Then we kind of get to the interesting part, the experiment phase, where we deliberately inject our fault. Last but not least, we verify and analyze all the data by comparing everything from the experiment part to the steady state. If our hypothesis holds, we've just built confidence in our systems. If it fails, We kind of discovered something there, a key vulnerability before a real incident could exploit it. And we kind of need to address those problems immediately. There are many tools out there, but for Kubernetes, Chaos Mesh is a game changer. You must kind of ask me why. Well, because it is fully open source. It has a lot of tools and plugins made by engineers for engineers. Second, it is fully CRD based, which means it doesn't only sit on top of our Kubernetes cluster, it lives inside it. By using this custom resource definition, we can assure that our chaos experiments are treated like standard cluster objects. We can manage it with tools we already know, like kubectl, to ensure that our fault infrastructure mechanisms are as simple as the cluster is itself. Besides that, we don't need any application code changes, or add some sidecars manually, or import any language-specific library. Chaos Mesh works at network and kernel level, which makes it transparent to our microservices. Last but not least, it supports all the GitOps workflows. Because every experiment is a YAML-based Kubernetes object, we can version control it alongside our application, require peer reviews, or use tools like Argo CD and Flux to automate resilience testing across our entire SDLC. Now we get to what we can inject with it. Even if we want to inject a network partition or a clock skew, Chaos Mesh covers the full spectrum. And it has a powerful UI, but we kind of don't use it because it's designed to be managed with GitOps and YAML. First, we are not just deleting pods. We are orchestrating the true reality. We can simulate pod chaos because if your application can't survive a network partition, it won't survive a regional outage. Second, we can get over our simple network connectivity issues and inject some surgical latencies and packet loss to show that our microservices won't just survive a network disaster, they will thrive in it. Third, we can use trace chaos to burn CPU and memory to force our HPAs and killers to show their hand before a real traffic spike does. Last but not least, we can go deeper to DNS and IO chaos. We can simulate resolving failures and some slow disks to show that a hardware hiccup won't just cascade in a total app blackout. Now it's time for the fun part, the boom phase, which I explained earlier. We kind of need to get our hands dirty here. I start the demo. I have a Kubernetes cluster with a microservices app. It kind of looks healthy, but let's see how much that lasts. And now from the Star Wars, let the chaos begin. Okay, I hope. Nope. Can I get some technical approach here? It doesn't work with swap displays. No, it's not a demo. I can be sure of that. How can I? Sorry. Okay, now getting into our demo part. I have 3 experiments prepared for today. I'll start the first one because it takes a little for it. The experiments are a little bit verbose, and we'll see the wheel I presented earlier. First experiment would be the network loss experiment. It's not Python, sorry. Okay. I'll leave it here on the half screen, and meanwhile I'll present our architecture. It's not a big deal. I want to make it bigger, but I don't know how. Okay. So we have 3 microservices, everyone with a different RPS. From service B to service C, we see there that is a steady 2 RPS. From service A, we have a burst RPS, and service C sends some random RPS. The thing I explain here is that we'll see some modifications in our graphics. I did it with some piplots. I didn't use tools like Prometheus and Grafana for simplicity. I didn't want to wait for Grafana to show my dashboard. So here I present you the first experiment. We get to a baseline phase, like the wheel I presented. And now we are getting to inject the chaos phase, and we'll have some errors here appearing to 1, 2, 4, 6, because what I said earlier about service B, we have a steady 2 RPS, so everything should be an even number, but because Python is scraping some data from the ping endpoints, we get it gets a little bit dizzy with the errors. Now we'll wait for our recovery phase to see that our pod is healthy again. Meanwhile, I'll show you the YAML for the first experiment. So, no, it's not service A. The YAML for the first experiment is here. So, as I said, the chaos experiments are standard cluster objects. Here is a definition for my first experiment. It's in my namespace named CND demo. I did a network partition to all the pods that are service B, and I terminated all the connections to only one of service C's pods. We see here that the experiment finished. I'll show you more about the verbose thing I spoke about earlier, but first I want to have the result in here. I have a chart. So, because I ended the connection between service B and service C, we see that the throughput for service B went down a lot. We have some latency there, but is not relevant because we have here some latency when the connection gets back up. So it's not relevant even in the last graphic that the latency is that big. I'll start the second experiment while I'm explaining because as I said, it takes a little. Okay, and the error rate spiked there. We don't see an error rate during all the chaos because I configured some timeouts on service B to see because all the experiments that target network loss also needs to have some timeouts because this is what we test when we use the network chaos. Okay. I'll show you the experiment 2. Okay, here as you see, I have a pod failure. The action is a pod failure, and keep in mind that is only one pod in the namespace demo, and it's service B, the one I target. Again, keep in mind that is only one. This is the only experiment that has the solution. Again, I didn't use any HPAs or anything like that for simplicity, and we don't need to see how the auto-scaling is happening. We need to see what the solution would be here. We are getting to the recovery phase for the second one. Um, okay, I'll show you also the script for my Python experiment. It's nothing too special here. It's just a method that runs the experiment. It's just a kubectl behind. It's just an apply, because we can use chaos exactly like the tools and commands we use for Kubernetes clusters. You can see here that I set the baseline and the chaos and the recovery state. Meanwhile, my experiment finished. So this would be the graphic. Again, because I lost one pod, we see that the error rate spiked because the service A has some burst requests. We see that the error spike went to the recovery phase. This is when Python scraped it, but it should be in the chaos phase. If we use those tools I mentioned earlier, like Prometheus and Grafana, it should be real time, but it takes some time for Python to realistically scrape the data. Okay, now we'll see the fix for this one. Because I don't have an autoscaler, I did a makefile to scale my pods to 2 replicas. As we see here, I scaled the service B to 2 replicas and will run the experiment for the fix. It's nothing different from the first one. Just I did it with a lot less time because we don't have some of the relevant data here. Okay. So I showed you everything from here, and I'll show you the services meanwhile. It's not something very special. I have a config map with some configs for my service. Deployment, nothing too important here to see, just some health endpoints and the memory and CPU I have for every service. All services looks the same. Just the configurations are different. And also here is my service and the port. Now getting to recovery phase in my fix. We'll have a little bit like 5 seconds. Okay. I'll see you the chart for this one. This should not happen. The error rate on that one would not happen, but because it scraped a lot earlier, it went to this experiment too. But we see that the throughput for service A didn't modify, and everything there should be fixed. Okay, I'll run the third experiment. Here is my CPU stress experiment. I'll show you right away. So the kind is a stress chaos. All the pods are selected for this one, and it's service C. The load will be 90, and the workers 4. I used 90 because I don't want to fully terminate my service C. If I put there 100, every request that is made to this service will fail. We can see that we got in the chaos phase. I have some more seconds here to wait. So I'll show you what I have in the chaos lib. Exactly as I said, I have some results directory and also just a kubectl apply for every experiment. I'll just give the name to the Python script and everything goes from there. And also the makefile that I talked about earlier, I did it again for simplicity, to not stay to use all the kubectl commands and use them to see it faster. I have the K9s here. As we can see, I scaled the service B to 2 replicas, so we have the 2 replicas in here. We'll not see anything about the connection, though. And we'll wait 20 more seconds for this experiment to get to the recovery phase. Okay. Also, I have the namespace here. Again, nothing too special about the cluster. Everything is focused on the chaos experiments we have here. Okay, the third chart looks like this. We don't have any errors because we still have 10% of the CPU, and that kind of processes everything. But we see in the third and the fourth graphic that the latency spiked a lot. Here it spiked on the first part, and there you can see the average. Okay. Getting back to our presentation, if I can manage to do it. Okay. I'll present you two big lessons to always keep in mind that everything should be controlled. First, do not start in production. Chaos engineering is not a cowboy move, it's a controlled experiment. You don't start by testing a new fire sprinkler system into a crowded building by lighting up a fire. You kinda need to do it in a test lab. Second, we need to minimize the blast radius, start with only one pod or only one single non-critical microservices, one single non-critical microservice. Third, we need to use Kubernetes native selectors like labels and namespaces to isolate our experiments. If your experiment crashes your app, you didn't perform chaos engineering, you've just caused an outage. Knowledge is the only KPI. We don't break things just for the sake of breaking them. We do it to uncover the hidden architectural flaws that only reveal themselves under pressure. The second lesson would be that chaos engineering without monitoring is just breaking things. We need to use tools like Prometheus and Grafana to show how and where the real problem is. The problem here is that the real achievement of chaos is not the crash itself, it's the forensic trail that's left behind. We don't just look at the down status and call it a day. We need to deep dive into logs and traces to see where our circuit breakers didn't trip, or where our load balancers didn't redirect traffic. Observability can transform failure into a real roadmap for improvement. Okay, as we wrap up, I want you to walk away with three fundamental truths. First, in the world of microservices, failure is inevitable. Any amount of architectural best practices can prevent it, but resilience is a choice we make every time we start testing your defenses. Second, we use tools like Chaos Mesh to make failure reproducible and manageable. We stop guessing how our systems might break and start showing how fast and steady they will recover. Third, and the last one, we integrate it in our CI/CD pipelines, making our manual daily checks into a real living standard in our engineering culture. Don't just wait for a disaster to show where your weaknesses are. Start experimenting, learn from it, and build a system that is truly fearless. Now some wise words from myself. Always remember that the test of a true engineer is not that they never have outages, it's that they are never surprised by them. My name is Bogdan Stan, and I hope you go home and break something today. Please don't take it too literally. Thank you.